Welcome back to a segment I'm calling Comparator Circuits with Op Amps. We're looking now at a basic comparator circuit with a reference voltage, and a Schmitt trigger. What we want to do is essentially ask or answer the following question. What happens without negative feedback? We've been assuming negative feedback. That gives us good properties. So now we're saying let's not have negative feedback. Let's not feedback that output signal to our inverting input pin of the op amp. What can we do, or can we now have working circuits under such a operating condition? So very first off, we won't be able to assume that we have this virtual short condition. That won't be there. So we no longer have this virtual short condition. That's now gone. So let's now look at what we can do if we are living in this condition without negative feedback. I've now drawn an op amp circuit. It has the positive power supply V sub P. It has the negative power supply V minus. So we're powering up this op amp with V plus and V minus. We have an input voltage, but this input voltage now is being applied to the non-inverting pin. We've placed our reference pin, we wired that to our common node or our ground condition, and we have the output voltage V sub 0. What are some general observations we can make? Well, the first is we can't assume this virtual short condition, so V sub n is not going to be assumed to equal V sub p. That's not going to happen. We're not forcing that to try to work because we aren't connecting our output terminal to our inverting input terminal on the op amp. So that's no longer available to us. We can also see in this configuration, the way it is set up, that our inverting pin is set to ground or to 0, and our V sub p is now the non-inverting pin of our op amp is connected directly to our input voltage V sub I. Keeping that in mind, and the fact that I sub p and I sub n, this hasn't changed. We still don't have any current going into our input terminals of our op amp, so that's good. Now what happens if we now apply a non-negative input voltage V sub I? Under the assumptions that we just made, or under the conditions that we just established, V sub n was equal to 0. We now know that V sub p is positive if V sub I is greater than 0, because V sub p is equal to V sub I. So now what do we know about this quantity? Well, A is huge. It's a huge positive number times a positive value, V sub I. We know now that this is bigger than 0. Well, if our output is bigger than 0, it's actually going to just rail. It's going to now, the output is going to saturate immediately. So V sub 0 is now going to equal our positive voltage supply rail. So our output saturates, and it's equal to the positive voltage supply rail when the input voltage V sub I is bigger than 0. Contrast that with the condition when V sub I is less than 0. Now we know that, again, V sub n is 0, V sub p is negative. That now says that this is negative. So now we can actually say that our output is going to go to the negative supply rail, or V minus. It saturates at the negative voltage supply rail. We can actually draw a picture of what's happening. let's say our input voltage V sub I is moving around in this particular fashion, we can now draw our corresponding output voltage from that comparator circuit. The comparator circuit is going to look at V sub I and say, oh, is it positive? If it is, then I'm actually going to equal V plus at the output. If it's negative, then I'm going to equal the negative supply rail. So now we've gone from V positive to V minus. These are supposed to be vertical lines that I'm now drawing. Then it goes positive again, and it saturates at the positive level. So you can see now that we've designed a comparator circuit. We compare the input voltage to 0, or what is really the voltage at the negative supply, or I'm sorry, at the inverting supply pin of our op amp. That difference now, we look at that, V sub P minus V sub N. If that's bigger than 0, then we saturate at V plus. If it's less than 0, we saturate at V minus. We now can say, oh, our output is going to be swinging back and forth based on what the input is between our V plus and our V minus in response to this input V sub I. So if we looked at that, we could say, oh, as long as V sub I is positive, then V sub O is going to have a value of V plus. If I now looked at a negative value for V sub I, then I would say, oh, then the output is going to be at this value of V minus, and that's true as long as V sub I, the input, is negative. So now I'm really just saying, oh, the output takes on one of two values, V plus or V minus. Which one it takes on depends on whether the input voltage is positive, it takes on V plus. If it's negative, it takes on V minus. We can actually change that up a little bit, and we can establish or put in a reference voltage connected to our inverting pin of the operational amplifier. Now, in this scenario, if V sub I is bigger than Vref, then that difference, Vp minus Vn, is going to be positive, and that then leads to our output voltage V sub I saturating at V plus. There's nothing to hold it down, so now our output goes to V plus. If the input voltage applied to the non-inverting pin of our op amp goes less than Vref, then the output will be the negative supply rail, which is V minus. Now we can actually draw what that looks like. Let's say that V sub I is noisy. So now V sub I is trying to be near Vref, but it's actually moving back and forth around that. That means that our comparator with a reference is going to be big here, it's going to be big here, it's going to be big here, which is maybe what we wanted because it's at Vref, but now it violently swings down to this V minus anytime that VI, or the reference input voltage, is a little bit less than Vref. And maybe we wouldn't want that. Maybe we don't want that to happen. So with noisy V sub I, we're seeing, in fact, that the output, V sub O, chatters. it actually chatters back and forth between plus and minus, or I'm sorry, between V plus and V minus. So we have this obvious question. Is it possible to keep the output from chattering between V plus and V minus for small changes in our input voltage V sub I around Vref? And you know, I wouldn't ask that question if I wasn't going to sort of answer it in the affirmative. So yes, we can do that, and the way that we're going to do that is we're going to introduce hysteresis, and we'll try to explain what that means into the comparator circuit with, in fact, positive feedback. And an individual with the last name of Schmitt actually introduced this concept almost 100 years ago, but it's now has his name, and it's the Schmitt trigger, and it looks like a comparator circuit with some resistors interconnected around the non-inverting pin. So now we're reinforcing the behavior of our output by feeding back the output to the non-inverting pin of our operational amplifier through this resistor R sub 2. So now let's analyze this circuit and see what this buys us. Does this eliminate some of the chattering that we might see in a normal comparator circuit by simply interconnecting a couple of resistors around the basic comparator op-amp configuration? And here we're simply letting the inverting pin be connected to ground just to make the analysis a little cleaner as we explain it initially, but Vref being not equal to 0 is possible, and we'll try to state that at the very end. But under these conditions, let's see what we have. First, we have our first observation that Vref is equal to 0. V sub n, the inverting pin, is connected to ground. Now, if V sub p again is the voltage at the op-amp's non-inverting pin. It's not the input voltage, V sub I. So now we're distinguishing between V sub p, the input to the non-inverting pin of our operational amplifier, and the input V sub I to the circuit that contains an op-amp. Now, if V sub p was in fact bigger than V sub n, then with this positive feedback, with the behavior being reinforced, we would, without that R sub 2 present, we would immediately go to the positive rail. But now we're saying, oh, V naught is positive. Let's just keep making, so we know that V naught is going to be positive, and we're just going to feed that back. That's going to try to fix V sub p as a positive value. So if V sub p is bigger than 0 in this configuration, then we still know that V naught is going to go to the positive supply rail. If Vp was negative, so it's now smaller than V sub n, then the operational amplifier still has this input-output relationship of A times V sub p minus V sub n. That V sub p minus V sub n is now negative times a big positive value A. That now says, oh, and keep reinforcing that, make V sub p continue to be negative, then we're going to say, oh, the output of our circuit is now at the negative supply rail. Let's see now the relationship between this V sub p and V sub I. What we're trying to do is try to keep this chattering from occurring when V sub I might be noisy and it's fluctuating around a given value. In this particular case, we're fluctuating around 0 volts for V sub n. So our reference voltage is 0. We want to know if we had a voltage around, if we had an input voltage V sub I fluctuating around 0 volts, are we going to be seeing this violent swinging between V plus and V minus at the output? So let's perform KCL at that positive or the non-inverting node of our op amp. We can say we have this current and we have this current, and again we have no current going into the non-inverting terminal of our op amp, so we now have the sum of those two currents leaving that node equal to 0, and I sub 1 is actually V sub p minus V sub I over R1 plus I sub 2, which is V sub p minus V sub O over R sub 2, and that's equal to 0. What is the value of V sub I now when V sub p is equal to 0? Again, this is now where we have this transition, because we know when V sub p is bigger than 0, we saturate at V plus. When V sub p is less than 0, we saturate at V minus. We now want to know what happens, or where is V sub I when V sub p is near this transition value of V sub p. Well, setting V sub p equal to 0 and moving the second term to the other side by adding V sub 0 over R sub 2 to both sides, we now have negative V sub I over R1 equaling V naught over R2. If we now solve that for V sub I, we see that V sub I is actually minus R1 over R2 times V sub 0. That's now what V sub I is, but V sub O, we know, is either going to be V positive or V minus. It's either going to be at the positive supply rail or at the negative supply rail. If V sub 0 is at V positive or at the positive supply rail, then V sub I, when V sub p is right at that 0 level, then V sub I has to be less than this new threshold condition of minus R1 over R2. It's no longer 0, it's actually a little bit negative, and it's negative by the amount determined by this ratio of resistors R1 to R2. So now we go a little bit below 0 before V plus is going to, or I'm sorry, before the output voltage V naught, which is at V plus, is going to switch down to V minus. So now we have a little bit of a transition region before we're not switching between V plus and V minus right at the origin or at 0. It's now going to occur a little bit below that. And if we draw that, we now say, oh, we are now with a V naught at V plus. We now go a little bit beyond 0. We go down to this new threshold value of minus R1 over R2 V plus, and once we go beyond that, then we switch and go down to V minus. So as we are decreasing in terms of V sub I, if V sub I is getting smaller, we're now moving V sub I smaller and smaller. Now when V sub I becomes 0, it doesn't dramatically drop down to V minus. We have to move V sub I down to this new threshold value of minus R1 over R2 V plus before we actually then switch, or before when V sub p becomes 0 and we go down to an output value of V minus. Contrast that with if we started with our output at the negative supply rail, V minus, then V sub I has to be actually larger than minus R1 over R2 V minus. So now we're assuming that V minus could be negative, but it's now going to be a negative of that value of V minus before V naught will switch to V plus. So now if we were looking at the input voltage getting bigger, then it's actually going to have to get bigger than 0, and it's going to have to get over to this value, which is now minus R1 over R2 V minus, before the output switches from the negative supply rail up to the positive supply rail. If we combine those, or let's say that we now just confine our attention to the condition where the magnitudes of our power supply rails are the same, and we just call that value V sub s, we can draw a little bit cleaner picture of this when we combine both of those previous pictures. We now know that if we're at V plus for our output and our input is here, then as the input gets smaller, we actually stay at V plus until we reach that threshold value, and let me just call it T. So now we're going this way, and we drop down and then go to the negative supply rail, V minus. But if we were actually at V minus and the input is now starting to decrease, then in fact we're going to stay at V minus until we reach that threshold on the other side, so this is now minus T and this is T. Now we have this region that depends on what our input voltage is at. So if somebody said, oh, my input is at 0.1, well, we don't know then if the output will be at V plus or V minus. We basically have to know, where did you begin? Did you begin at V plus and now you're at an input voltage of 0.1? Then you would stay at V plus. But if you were actually at 0 and you moved to V sub I of 0.1, then you would be down here and you would be at V minus. Where this picture now shows us this hysteresis pattern, that it depends actually on where you came from relative to where you are at with your output. If you're coming in this direction, then you continue past 0. Remember, our reference voltage in this example was equal to 0. We go beyond 0 before we actually transition into V plus. And this, in fact, will keep us from chattering back and forth. Now if our noise on V sub I remains in this region, then we are not going to be switching back and forth between V plus and V minus. If we were down here, we would just stay down there as the input is moving back and forth around 0. Or if we were here and we moved into this region and we're moving back and forth, we stay at that output value for our op amp in this Schmitt trigger configuration. One last comment is you can actually provide this hysteresis behavior around a non-zero reference value, and you could now rederive that same relationship, except now you need to realize that V sub p is equal to a different value, because now you have this reference voltage at the inverting terminal and not a value of 0. So now you would be looking at, oh, V sub P now needs to be bigger than V ref before we go to the positive supply rail, and V sub P needs to be less than V ref, and you could then look at what V sub I needs to be, and you'll see this same hysteresis pattern behavior in this scenario. That should give you now a little bit of a background on Schmitt trigger and determining the threshold voltage needed to allow you to avoid this chattering back and forth when you have a noisy input signal applied to your comparator circuit.